Hydrology, Open Channel Flow, Chapter 10, Lecture 1. I'm Dr. Marty Matlock. We have a number of support documents for this lecture. The two we're going to focus on predominantly are from the National Engineering Handbook, Part 654, Stream Hydraulics. Stream hydraulics is a combination of science and engineering for determining stream flow behavior at specific locations for purposes including solving problems that generally originate with human impacts. So it's fixing messes we make. The discipline of hydrology involves the determination of flow rates or amounts, their origins, and their frequency. You know that very well. Hydraulics involves the mechanics of the flow, and given the great power of flowing water, its effects on bed, banks, and structures. So hydraulics is the management of that flow. The flow depth is the distance between the channel bottom and the water surface. We're going to be doing a lot of definitions. You'll find all of these in the supporting document, which you have available in the end links. You can find it to download. It's also available to you through the course documents. For rectangular channels, the depth is the same across an entire cross-section, as you know. And those are channels we design. They don't exist in nature. But it obviously varies in natural channels. Depth is often measured relative to the channel thalweg, which we know as the valley way. It's the lowest point of the channel. The normal depth is the depth of flow in a uniform channel for which the water surface is normal or parallel to the channel profile and energy slope. So a normal depth is a channel, basically, as you see here, at full depth. Now you see you could get higher on this side, our right-hand side of the channel. Water could go higher and not be out of the banks, but when it does, it'll be out of the banks on the left-hand side. And so we typically consider the lower bank top to be the bank full depth for the system. For a cross-sectional line, so the stream lines of flow are perpendicular, which is the way water flows. The flow area is the area of the cross-section between the bed and banks and water surface. All the cross-hatched area is the water surface. By the way, this inverted triangle with three lines, and the three lines are usually not square, just equal length. They usually make a triangle too. That point where the bottom of the triangle is the depth line. That's the point where that shows the water depth, and it's a very specific indicator in map making and in diagrams. For rectangular channel, flow area is depth multiplied times width, because it's a rectangle. For a natural channel cross-section, the area may be approximated with the sum of trapezoidal area between cross-sectional points. We often would estimate this sort of a channel as a trapezoid, basically slope down to some bottom, cross-section to bottom, and then slope to the top. And sometimes we underestimate the thalweg depth a little bit in doing that and overestimate the width doing that. But that's an easy way to approximate this. The top width of a channel cross-section is the water surface, typically designated as T, and it's a factor in hydraulic depth. So all of these definitions show up later. Area D max, wetted perimeter P, top width T. Notice that we're using the same. It's confusing because P is precipitation, and in our watershed hydrology. So you have to understand the context for the use of these letters. We know that the flow, which is L3, cubic feet, cubic centimeters, cubic meters per unit time, second, minute, hour, day, year, through a cross-section of stream, and we usually indicate these as A to A prime, B to B prime, etc., is equal to the velocity, that's feet per second, or meters per hour, times the cross-sectional area, and that's square feet, square meters. Q equals VA. Simple, 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 and you will forget it and get messed up. Remember this, Q equals VA. You're trying to figure out how much Q is coming out, and you know velocity, and you can calculate area, you can calculate Q. You know area, you can calculate velocity, you can calculate Q. If you know Q and you know area, you can calculate velocity, etc. A flow through these channels is not, because water's weird, as we discussed at the very beginning, because it has So it's coherent or cohesive, strong cohesive forces. When water is flowing, it at different velocities it exerts or expresses itself differently around the materials it's flowing through. We use the Reynolds number as a dimensionless ratio calculating the relative effects of viscosity to inertia. It's used to determine whether a fluid flow is laminar or turbulent. Laminar flow, of course, is flat flow over a surface. Think about slow flow over a sheet of glass at a slight angle. That's laminar flow. It means layer flow, like laminar clouds. Turbulent flow happens when the Reynolds number gets high, when velocity gets high, and then with the relative kinematic viscosity of water, then turbulent flow occurs, and you start getting, just like with gas and with clouds, you start getting mixture and non-linear flow as it hits surfaces, especially the bed surface and rocks and other things. And that actually decreases the velocity. Inertia is the product of velocity and hydraulic radius. It's just mass is moving at a velocity, and then you're trying to stop it. So it's divided by the kinematic viscosity of water with units of length squared per time. A Reynolds number of less than 500 is laminar flow. Reynolds number of greater than 2,000 is turbulent flow. Values between these limits are identified as transitional. You guys all had fluid mechanics. You understand this already. But I want to make it clear. In streams, we're almost always dealing with turbulent flow because we're dealing with water at standard temperature and pressure, and we're dealing with open channels. And that is to say, atmospheric pressure. So we're almost always and relatively high velocities, not dramatic velocities. Our slopes are almost always less than 10%. But because of that, we're always dealing with turbulent flow. Laminar flows usually only occur as water is flowing across the surface into the streams. But turbulent flow is occurring in the streams. For use in sediment transport analysis, the Reynolds number has been formulated to apply at the sediment boundary, water boundary. In this case, the velocity is local to the boundary and termed the shear velocity. That's V sub asterisk. That's the shear velocity. That's important because the shear velocity is what shears material, is the force of material on the bed, which determines whether the material is eroding or not. Are you eroding the bed material? And if you're designing a bed and you don't want it to erode, a stream bed, you don't want it to erode, you got to be able to predict this. You got to be able to determine what size particles you want to put on that bed so that it stays put for a design flow, a 10-year flow, 100-year flow. You can also use this to predict how much erosion will occur during specific flow events for natural systems that you didn't design. The length term is not the hydraulic radius, but roughness height or diameter of particles, D, forming the boundary. So the D here is the particle diameters. Again, context. I'm sorry that we need about 50 more. We need to use more Greek and Russian and Chinese letters in order to make all of these equations so they don't overuse the same letters. So the boundary Reynolds number has also been called the bed Reynolds number or shear Reynolds number, which is what you see here. The boundary shear velocity times the particle diameter over the kinematic velocity. Because stream flow is almost exclusively turbulent, the Reynolds number is not needed as a flag of turbulence. We don't use it to see if we're turbulent or not. We use it to determine if sedimentation is occurring. If the drag coefficients have been empirically related to Reynolds number, which is used to calculate sedimentation, shear stress, and sediment movement. This is by God engineering. Is the bed going to erode or is it going to deposit material? So as we evaluate the potential for water to move Earth, the Reynolds number is one of the most important variables. The Froude number is another dimensionless ratio relating inertial forces to gravity. So the Froude number equals velocity over the square root of acceleration due to gravity times flow depth, little d. Represents the effect of gravity on the state of flow in a stream. So if the Froude number is less than 1, gravitational forces dominate and the flow is subcritical. If it's greater than 1, inertial forces dominate and the flow is supercritical. You got to get this you got to have in your head when you look at a flowing body of water, you got to be able to say, oh, that's a Froude number of less than 1, or that's greater than 1, and understand what that means in terms of what's driving flow. Is it just the gravitational difference between upstream and downstream of the point you're looking at, or if there's a inertial force of the mass of water above that water that you're looking at and pushing it downstream? Is it being pushed or is it flowing? If it's being pushed, the flow is supercritical. That is, if inertial forces are driving it, it's supercritical. The Froude number is used to determine the state of flow, since for subcritical flow, the boundary condition is downstream, and for supercritical flow, it's upstream. That is, if you want to control flow conditions and supercritical flow, you got to go upstream where the water's pushing in order to control it. You can't just control it at that point or downstream of it. Downstream, you can put in a dam or a structure, a flow control structure, or something else in a subcritical gravity-driven flow system to control flow. So when the Froude number equals 1, the flow is at critical state. It's at that transition. There are all sorts of YouTube videos for critical flow. Critical flow occurs when the inertial forces are exactly equal to gravitational forces. That's when it becomes critical. Subcritical flows are calm, deep waters where surface waves can propagate upstream. Supercritical flows are in shallower, faster waters where surface waves can't propagate upstream. Hydraulic leaps or jumps occur when the flow goes from supercritical to subcritical, when moving water hits still water. The release of kinetic energy as the fast-moving supercritical water comes into contact with slower-moving subcritical water cause some of the cohesive forces that usually hold water together to be forced apart. So you get foaming, you get froth, you get what we call rapids. But there's another phenomenon that occurs here too. Let's take a look, see if we can play this video within the embedded film. Kayakers going over a waterfall where you have supercritical flow. Look at this laminar flow. That's laminar flow. Then this water's coming down at high velocity because it's laminar. Then it hits this subcritical water. See the foam? So what's going on with these guys? Are they playing? Well, maybe, but not necessarily. Kayakers are killed every year in these traps. These are called hydraulics. And see that hand up? He's looking for help. He is being shoved underwater. He's wearing a life jacket and he can't come to the surface. This is the force and power of water. Water is incredibly powerful. It's incredibly heavy, and when it has high velocity, it has incredible force. He gets out alive. We'll stop there. Let's just close that tab. Go back to here. So, when the Reynolds number is less than 500, we have laminar flow. Over 2,000, you have turbulent flow. When the Froude number is less than 1, you have subcritical flow. Over 1, you have supercritical flow. So what we just saw in this video was critical flow with a velocity Froude number of 1 coming right over a crest. Water was laminar coming down, which means it can accelerate because there's very little turbulence and it's moving in straight lines. Then it hits this slow moving water, subcritical water. It has supercritical flow velocity. Overflow jet with maximum velocity and force hits, and it creates this reverse rolling. It's called an entrapment zone in a boil area. These air bubbles also that are entrapped here make this a cubic meter of water weigh less than than a metric ton, than 1,000 kilograms. It can weigh as little as 800 kilograms, which means it's low density water, which means you don't float. Air bubbles reduce the buoyancy, and subcritical flow velocity then occurs up here. The gravel and stones deposited naturally by the streams over the time create this pinch point, this convergence, which slows the velocity down, and that's what creates this entrapment zone, these hydraulics. You can design these too, by the way. Conveyance K is a measure of the flow carrying capacity of a cross section, which is directly proportional to discharge. So, conveyance typically is designated big K, may be expressed from Manning's equation without the slope term as K equals 1.486 over Manning's N times AR to the 2/3, where R is the hydraulic radius, which you know about, or K can be expressed in terms of Q over square root of S, where S is slope, feet over feet, meters over meter. So K is pretty straightforward as a conveyance variable. Streamflow hydraulics. The hydraulic depth is the ratio of the cross-sectional area of flow to the free water depth or top width. Free water surface or top width. So the hydraulic depth D is generally used in either computing the Froude number or in computing the section fraction for critical depth, like we've discussed earlier. Since only one critical depth is possible for a given discharge in a channel, the section factor Z can be used to easily determine it. So critical depth equals Z to the G, or square root of gravity, and Z equals A over square root of D. So critical depth equals A over square root of D times square root of gravity. For cross-sectional section normal to the direction of flow, that is perpendicular to the direction of flow, the wetted perimeter, typically designated P, is a length of a cross-sectional boundary between water and bed and banks. So the wetted perimeter is the boundary from the top of the water all the way around. The hydraulic radius is the ratio of the cross-sectional area of flow to the wetted perimeter. So all this cross-sectional area divided by wetted perimeter gives you the hydraulic radius. If it's a circle, it's just the radius, by the way. The hydraulic radius R equals A over P is used for Manning's equation for calculating normal depth discharge, as well as calculation of shear velocity, which is what we use the Reynolds number for. Velocity is a physics term for a change in distance during a time interval. You know that. Flow velocity refers to the areal extent of the flow in a cross-section from which a velocity is specified. For example, an average velocity that applies to an entire cross-section may be determined from V equals Q over A if the discharge is unknown. A uniform velocity may be determined from Manning's equation. There are a number of ways to do this. We can measure it, we can model it. Determining the state of flow is a matter of determining whether the velocity is greater than the critical velocity, V sub CR, or less than the critical velocity. And this should start to look familiar to you. Critical velocity equals the square root of gravitational acceleration times critical depth. Now let's talk about some other characteristics, and we're going to switch to the hydraulics reference manual for HEC-RAS. HEC is the Hydraulic Engineering Center of the U.S. Army Corps of Engineers. RAS is the River Analysis System. So when we talk about HEC-RAS, we're talking about their model. Remember, water is heavy, it's cohesive, it accumulates in channels, it flows through channel based upon an energy gradient. Gravity drives the flow, or mass, inertia. It has momentum, inertia, force. Conservation of mass and energy for a stream segment following a true Flow out equals flow in plus water stored. Energy in equals energy out. Velocity on open channels is maximum at the cross-sectional area of the channel with the most momentum and least friction. So if we look at these two different channels, think of a channel as this box where water's coming in from the watershed, some rain's falling on it, and it's depending on the size of the river. For the rivers we deal with, mostly they're smaller than this. Water's coming in from upstream, water's going out from downstream. The water coming in from upstream can push the water downstream if you're at supercritical flow. And you have, of course, bank full widths. You have the forces upward, force down to the weight of water, force up. And so you have some base flow coming up too from the stream. So if we look at a river cross section A to A prime, the straight river, you can see that the maximum velocity is just under the surface in the middle of the stream because you got friction across the boundaries here. Friction as the water flows across whatever this bank is made of, and it could be made of glass with very low friction, or it could be made of vegetative material with very high friction. That influences either way, they influence the flow of water. Even the surface of the air, friction of water moving under the surface of the air affects the velocity of water. So your maximum velocity is below the surface. When you have a bank turn, remember we have momentum pushing the water, so the water turns, that momentum keeps pushing the water this direction. So you have water building up against this outer bank, velocity building up against this outer bank. That's why the outer banks erode. That's why the inner banks turn into gravel bars, because they deposit because of that momentum. Generally, we can say that the maximum velocity occurs at right at the surface, or right under the surface of a cross section, like you're seeing here, or it occurs, and the average velocity is about 0.6 of the depth. If the depth is y, about 60% of y is where you get the maximum or the average velocity of the river, if this is a velocity profile. So kinematic and dynamic waves are important to think about too, in terms of these critical variables: Freud number and Reynolds number, Froude number and Reynolds number. Kinematic wave is caused by accumulation of water in a channel where H equals increase over time. So the kinematic wave occurs when you are subcritical. You have subcritical flow. And so if you're here and you're at you have cameras set up at two different places, and flow is increasing, and you see flow increase equally up and down at the same time, it just looks like the river's rising. That's a kinematic wave. Dynamic forces of water equals friction to the bank, so the water level is level. There's little acceleration of velocity. You get this dynamic wave, though, when inertial and pressure forces, when you have critical flow, inertial pressures are greater than friction forces, creating unequal and non-steady water surfaces. And that's when we see this, what we saw in the video earlier, this dynamic wave. We're going over the crest, so you have deeper water at the back. The actual depth of the water is driven by pushing of water down. That's supercritical flow. Translation of a wave is the downward movement of the wave without changing the shape of the hydrograph. That's what we see in A. So that would be subcritical flow. This process is dominant over short distances and narrow channels. Attenuation of a wave changes the shape by reducing the peak and extending the base. A flood wave in a river channel is subject to water storage on the banks, translation of the wave downstream, and attenuation of the wave as the channel opens. So this is what we normally see, is that from upstream to downstream, we see a particular peak flow event from a rainfall event, for example, changing as the water moves downstream. If it doesn't change at all, if it rains upstream and downstream doesn't change at all, it's a trough. And that water is just moving through that trough. Most of the time, our natural channels are different than this. Now you see these troughs, to be clear, you see them in nature. You see them in arroyos and canyon lands in particular, and that's why they can be so deadly, is suddenly you can get a little bit of rain upstream and you can get a flash flood very quickly. So let's think about this in terms of energy. If we look at a cross-section with surface water flow here, and we have some energy grade line, which is this dashed line. So we have the surface of the water. The energy grade line is is alpha V squared over 2, that's upstream over 2G, for depth Y2 of water, and Z2 is the difference in elevation, so from data point. Then downstream we have Z1 data point, Y1 is the depth of water downstream, alpha V squared over 1 downstream is the velocity of water downstream 2G, and we have the difference in this energy gradient between the water surface and alpha V squared over 1 2G. The difference in these two is the energy grade line. Now, it's not really an above the atmosphere phenomena. It's just we're looking at alpha V2 squared 2 over 2G and alpha V squared 1 over 2G. And then the difference between those two equals hydraulic head. So that's what you're seeing here. This is Bernoulli's equation. It's another way to think of Bernoulli's equation, which is the energy equation. It's an old understanding. We use it in fluid dynamics. It works in rockets and it works in rivers. Where Z1 and Z2 are elevations of the main channel inverts, and invert is the bottom. So the invert's the bottom of the channel here, Z2, the bottom of the channel 1, Z1 downstream. Y1 and Y2 are depths at cross sectionals at these points. This would be A prime to A, B prime to B. V1 and V2 are average velocity differences. And then alpha is the velocity weighting coefficient. That's usually 1, by the way. Gravitational acceleration, G, and then energy head loss, H sub E, which is calculable. So we can know all these things. These are all knowable or extractable or measurable. It means we can understand the energy of a river. The energy head loss between two cross sections is comprised of friction losses and contraction or expansion losses. So this is the equation for a head loss, which is H sub E up here. So it's the discharge weighted reach length times the representative friction slope, which we'll return to in a moment, plus C, which is expansion or contraction loss coefficients, times the absolute value of the differences between these characteristics, upstreams and downstream. The distance weighted stream length, it seems like it's easy, right? But rivers are complicated things because the cross-section of a river is never a trapezoid or a triangle or a square, unless we made it that way. Mostly it's a bunch of different shapes, and it's usually a main channel with side channels or with side banks, left banks and right banks to be specific. So if we look at a left overbank or overflow bank, a right overflow bank, and a channel, you can see you can get lengths of the three of those, and you average those up and get with the average flow in each of those three channels, and that's how you get the flow weighted length. Here's what that looks like. Total conveyance and velocity for cross-section of a stream requires that the flow be subdivided into units of uniform velocity. And that means usually uniform Manning's N, because Manning's N, the roughness coefficients, are what determine the velocity, aside that and the slope and the few other things. But Manning's N is really, if you standardize that, you captured most of the uniform velocity. The flows through these, so you take a channel, this is a typical cross-section of a channel. You can see where you can have area 1, P1, which is the wetted perimeter, area 2, P2, area channel, P channel, area 3, P perimeter channel 3, with 4 different Manning's N, 1, 2, 3 in the channel N. And you can calculate K's for those. K equals 1.486 over N times AR 2/3. We know what, we've seen this before. A is the flow area for the subdivision. R is the hydraulic radius. It's area wetted perimeter. SF sub F is this, then can be calculated once we know K and we know Q, then we can calculate the slope of the energy grade line. Flow in the main channel is not subdivided except when N is changed within the channel area. Now, we try not to do this in our systems, but sometimes N is the channel is just big and weird, or big and non-uniform. So for the determination of N of the channel, the main channel is divided into different parts, just like the others, and each with a wetted perimeter Pi and the roughness coefficient N sub I, and you come up with an average Manning's N for the channel. We generally, in smaller streams, simplify this as the channel wetted perimeter, because usually the channels are gravel and rock with maybe some soil side slopes. And then these beds sometimes are vegetated, sometimes they're not, sometimes they're gravel. Oftentimes they're vegetated with grasses, sometimes even things like river cane. And sometimes in the floodplain, this will be forest land. So you got to understand what those are, depending on what depth flow you're predicting, because many times this is where the riparian forest exists. Remember, we talked about the kinetic energy head. We can calculate that. We generally model smaller rivers as in one dimension, which is a linear thing, linear flow. Single mean energy of flow is computed at each cross section. But you can do that for different areas, for different depths, and you can also calculate them for different parts of the channel. Water's moving more slowly in the vegetated side channels than it is in the unvegetated straight or river channel, for example. So we can get different velocity profiles, and different depths give us different velocity profiles. The mean kinetic energy is calculated using a head-weighted coefficient alpha, where alpha equals flow times velocity squared at cross-section 1 plus flow times velocity squared at cross-section 2 over flow at 1 and 2 times the average of velocity squared. Another way to calculate alpha is using the three different K's. So this gives you an kinetic energy head for a particular cross-sectional area. Friction loss is the product of friction slope and L. So friction slope and L, so S of F is a friction loss coefficient. There are many ways to express it, which leads to confusion. Make sure you understand which way you're using and why. As a function of Manning's N, S sub F equals Q over K squared. Simple. That's derived from the previous relationships. The average conveyance is just the average S sub S over Q1 over K1 plus Q2 over K2 squared. Simple, add them all up and then square them. That's the average. The average friction slope, that's for cross section, equals the SF1 plus SF2 divided by 2. So one's a conveyance slope, one's a friction slope. The conveyance slope is the one we mostly use. The other is a friction slope. There's the geometric mean and the harmonic mean. We typically use the average conveyance equation for S sub F. It's the easy one to use. The mean kinetic energy is calculated using a head-weighted coefficient. That's alpha. Alpha varies with uniformity of velocity vectors in a cross-section. For fairly uniform velocity, it's generally 1. If velocity varies markedly over cross-sectional area, it can go as high as 1.1. Specific energy is a particular concept in hydraulics defined as the energy per unit weight of water at a given cross-section with respect to the channel bottom. So now this is where we get to this issue of critical depth, critical flow, critical velocity. If we look at depth relative to specific energy, as specific energy goes up and depth goes up, we have this dashed line. And beneath this dashed line, we have different states. We have a range of subcritical flows and then a range of supercritical flows with Froude numbers. And you can see that we have Q higher than Q1, this blue line. This black line, A is a given flow rate with Q1. That's the cross-sectional area at a given flow rate. And the red line, Q is lower than Q1. And across the two of these, we have two different depths, D1 and D2, specific energies. So the relationship between these, I think we've discussed pretty clearly. Specific energy at any cross-section for a channel of small slopes, and alpha of 1 equals y plus v squared over 2g. So points D1 and D2 are alternate depths from the same energy level. Same energy level, but as the water gets deeper, its as the depth increases, you go from supercritical to subcritical. So we have a number of web resources for you to take a look at, a lot. Army Corps of Engineers HEC-RAS workbook and page. Open Topography is a good link for topographical sources. USDEMs, which you've already used, but it's a good reference link. NRCS National Stream Restoration Design Handbook is one of our best resources for moving into stream work, especially Chapter 6, which we used extensively in this lecture. Thank you.